Okay, everyone. Hopefully we're got started this time. Sorry for slight technical difficulties. So I've had the opportunity to introduce Chris Rackauckas, who has many jobs, including VP of Modeling and Simulation at Julia Hub, Director of Scientific Research at Puma's AI, and he's also co-principal investigator at the Julia Lab. With all Chris's experience and for employment here, he's going to give us a great talk on open source component-based modeling with ModelingToolkit, where we're going to learn about putting ordinary differential equations back in machine learning as part of the Julia SciML ecosystem. So without further ado, here's Chris.
Yep. Hello. Thank you very much, and thanks for having me. So today, what I want to talk about is Modeling Toolkit, which is an open source library for component-based modeling, right? And there really isn't an analog in the R or Python space, so I think that this might be kind of a new topic in the PyData kind of world. So I think what I really want to spend my time doing is really just describing what is this all about? What is component-based modeling all about? Why should you care about it? And what's the look and feel of a component-based modeling tool? And also, why did we decide to develop this on top of Julia, right? So, what is the purpose of this whole field, right? The idea is model composition, right? So let's say you spend 5 years developing a model of a vehicle for your PhD, right? You have this intense model of a car that models how the drivetrain is connected to these engines, and you then have all these little pieces in there to be able to say this is my model of a car, right? And there's somebody else that you don't even know that spent their 5 years of their PhD modeling a battery, right? Everything about the electrochemistry, the different electrolytes, and maybe it's like a solid state battery or an NMC kind of chemistry. All these little details about the batteries, right? And so, what we really want to happen in the world is we want to be able to say your expertise of battery modeling and your expertise of a car. Well, I want to build an EV. So, what do? I take your car battery, I stick it inside of and I stick it inside of my car, and now we have a much better model that is modeling the reality of all these other components. If you think about it, you really need to do that all the way down, right? Because a car has, an engine, and there's people that spend their entire life trying to understand how different types of engines work and the efficiencies and how all the and the thermals are working, right? There's an HVAC system of the car. There's all these little tiny pieces. So it's not really just like just these two models, but instead what you really want to do is you want to take the expertise from 20 different people building completely separate models and want to just say, plug all models together, generate solver, and solve. And now, what does my digital twin of the real world object truly look like? Now, that is how you would bring computation to being something that is not just toy models, not this, I built this little tiny model for a year, or something as my master's project. No, this is something that would be able to try to get you to multiple digits of accuracy of real world devices, right? Um, Now, what's the issue here? Well, the issue is that the way that you actually write down models looks like this, right? I just kind of pulled two screenshots of different websites where you just say, hey, what is a basic weather model? And they say it's the Lorentz equations. And you say, oh, what is a basic model of predator prey dynamics, for foxes and rabbits? Oh, it's Locke-Volterra equations, right? You write these down as ordinary differential equations normally. Sometimes they're optimization problems, sometimes they're nonlinear systems, but and we'll get into all that bit. But really, the key is you write down equations to be able to do this. But well, in your head, you have equations, but you write down code, right? And so code is something that's very difficult to kind of put these things together because let's say I now want to put the weather model and the predator prey piece together, right? What should happen? Well, maybe something about this weather model should influence the rate of growth of rabbits because, well, I mean, it's changing the food supply and all that. Well, how do you actually put these together? Ends up being a very manual kind of thing, right? Someone needs to understand both models and be able to plug the two together, define relationships between variables, and this then becomes something that is almost as hard as creating a new model itself, right? And so if you work in any of these scientific labs, you might have seen, your lab might have this old Fortran code that has existed since 1980, where what you do is when you have a new idea, you do a modification to that code base until, you do your piece, and then, that's your PhD, and then the next person modifies it. But you're always just trying to modify the same piece of code because putting together two independent codes is impossible, right? And so this is exactly the problem that Modeling Toolkit is solving, right? Because really the question is, how do I compose two models, but make sure that I get a fast and stable way to be able to solve it, and then be able to actually run, real scalable solvers on the composed part, right? So hopefully that sets up what this is all about. Now, this is what it looks like in practice. So here, for example, is an RC circuit model, right? Very basic model. But what I'm saying here is, oh, take the resistor model, instantiate the capacitor model, instantiate a constant voltage source, and instantiate a ground, and now connect them like this. Connect the constant voltage source to the resistor's positive pin, connect the resistor to the capacitor, so I connect all these models, and then I just say generate the whole thing together. And it just goes, okay, I know that here's the voltage, and I'm going to explain a little bit in a little bit how it knows how to do the composition, right? But it kind of takes all these ideas of all these little models and says, oh, I know Ohm's law. Oh, I know, the capacitor equation. And so therefore, the complete system is one ODE that looks like this, right? And now the key is that Modeling Toolkit is able to do a lot of symbolic transformations because there's a lot of numerical details that are required to make sure that the system that you get is actually solvable, right? Because if you think about it, what a lot of people spend their time doing is being able to say, well, on my equations, I need to do this special thing. On my equation, I need to do this special thing. And what we've been able to do is we've been able to extract out what are all the special tricks that people are doing, and can we understand those as symbolic algorithms, right? Can we just prove like, oh, you need to do this trick when your Jacobian is structurally singular with respect to yada, yada, yada. Now it's no longer domain specific tricks, but now there's symbolic, numeric, reproducible, composable passes that we can do to be able to transform models. And now, if we can do all that, then all we need to know is what equations to constitute your model, and we will generate the good way to solve it for you. And that is really the core of what Modeling Toolkit is all about here. It's this symbolic layer to be able to compose models and then be able to make it easy to be able to efficiently simulate from them, right? So how does it actually work? How does it actually work, right? Let's go into some details. So the way we do this is with something known as acausal modeling. This is something that was first pushed forward by the Modelica community back in about the 1980s, and it really requires a lot of symbolic numeric underlying tooling in order to pull it off, right? The reason why it's used is because it's a very efficient and human and computational time, because it allows you to be able to independently build your models, and then the composition process takes care of how to actually compose and get a stable model from the different pieces. So I think the best way to explain how acausal modeling works is a show don't tell kind of approach, right? So what I want to do is I want to just show you how do you actually do RC circuits? How do you do circuit modeling with acausal modeling, right? So the way that you've probably done RC circuit before, if you took a physics class, you probably derived what the equations are for the RC circuit. But let's actually go through this process, right? So if you think about what we have here, right? We have we have a resistor, right? And the resistor itself has a voltage. The voltage across the resistor is defined as the voltage of the resistor. And what we say is that, okay, the voltage of the resistor is equal to the current through the resistor times the resistance. This is known as Ohm's law, right? If you remember back to your physics classes. And now in the capacitor, you have the capacitance equation, right? That the current into the capacitor is given by a differential equation with respect to its voltage, right? And now you also know Kirchhoff's voltage law, which is that the voltage in a loop sums to zero, and that you have Kirchhoff's current law, right? Which is that you have the currents at different parts that are connected. Any electron that is flowing this way is an electron that you have to conserve flowing this way, right? So the current coming out of the resistor is the current going into the capacitor, right? So this is your basic physics, and you learn these facts in isolation, right? Oh, this is how Kirchhoff's laws work. This is how a resistor works. This is how a capacitor works, right? And now when you piece all these together and you say, okay, now I have a constant voltage going into the system, what is the dynamics of this complete system, right? Well, what you probably did in your physics class is you probably wrote all these equations on the board and you just said, well, we need to solve for what VC dot is, right? That's our differential equation inside of this system of equations. And so you do a bunch of substitution, yada, 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 and you say, this is the RC circuit, right? Great. So that's how you do modeling, right? So you do this on the whiteboard, and then you go to your ODE solver, you type in this ODE, and you simulate it, and there you go. Now you do modeling, right? This is how we do it. Now the issue is I forgot a slide in here, but the issue is now that if you put in, for example, a current source, then all of your computations are different here. If you put in if you put in a what's the word, an inductor, then a lot of your computations are different here. And then, you might end up with two differential equations instead of one. And every single time you change one thing about the model's definition, you have to redo this derivation, right? And so the real question is, well, this derivation is a computational process itself, right? Finding out what to solve for is just a property of these equations, right? The true description of our system is all four of these equations are true, dynamics happen, right? And so what we want to do is we want to go from this description of all four of these equations to just say, this is what the solver needs to solve. Please solve it, and now be able to interact with the system because we know everything about the system if we have solved for the time dependent part, right? And so this is then how acausal modeling kind of works. This is the first way of describing how it works. Again, I give a 3-hour workshop on really trying to understand it in detail, but this is part one. I'm going to do part two where I go back through the equations, right? But what you see here is that when I put together, I say, hey, define a resistor, define a capacitor, define ground, connect all this. Now I have an ODE system from all that and simplify it, right? The structural simplification is a form of a symbolic computation on the model. And what it says is when I print the equations, it says, oh, here's the differential equation. This is all it is. This is all you have left, right? What it's effectively able to do is it's able to take all of the equations that we have and be able to figure out this is what I actually need to solve for. It does this computation somewhat behind the scenes, and then it says, hey, you have four equations, but I can bring it down to one. I solve this one equation, but importantly, it then gives you an interface to be able to handle the fact that you don't necessarily need to know what was solved for, right? So this is solving a differential equation that is only with solving one thing, which is capacitor dot v, right? Because that is the differential variable. But what if I care about the current going into the resistor, right? Well, what it's able to do is it's able to say, well, if I know this, then I know this, and know this, and then it can reconstruct. If the only thing I know is VC, then this is how I calculate IC, and IC equals IR. So therefore, I know how to be able to get the current to the resistor, right? And so this is then changing the way that we're thinking about building a modeling script, right? Instead of saying, oh, I'm going to write down my ODEs, what we do is we write down, just what equations we have. We tell it to solve it, and we tell the system symbolically what we want to get out of it, and it's able to then regenerate all of the different equations to be able to do the computations you're truly asking for. So now let me go one step a little bit deeper. How did the A-causal model actually work, right? Because I haven't really told you too much about, how would you define a component yourself. So the way that acausal modeling works is actually fairly straightforward, and it's this observation that there's a conserved property throughout physics, which for any Hamiltonian system, you always have two types of variables. When you think about the Hamiltonian system, you always think I have p's and I have q's, right? And you have your dH dp, you have your dH dq. Right? But fundamentally, there's actually something conserved across all of this, right? Which is that if you think about it, there's two types of variables. We have something called across variables and through variables. Across variables are things that when you connect, they're equal. And through variables are things for which they sum to zero. So what do I mean by that? So when you connect two pieces, right, the current is always going to be equal because whatever electrons are flowing from the left to the right, it leaves one device and goes into the next device. So connecting two things means the currents are equal. And then the other thing is that when you connect to, or sorry, when you connect when you connect to two devices, the voltage on the left and the voltage on the right are going to be the same because the voltage drop at a given pin is always going to be equal, right? You only have a voltage drop across objects. So whenever you do a direct connection, you always make equality of your voltages. And whenever you then connect to things as well, you always have that whatever's flowing out of one side is flowing into the other side, which is to say the flow out plus the flow in is equal to zero because if by sign convention, flow in is negative, right? And so, why is this important? Well, it's important for multiple reasons. One thing is that it's a restatement of Kirchhoff's voltage and current laws to be about conservation, right? Kirchhoff's current law is just conservation of electrons, right? That they don't disappear as they're moving. And Kirchhoff's voltage law is conservation of energy. And locally, conservation of energy and conservation of current just means that voltages become equal and currents always sum to zero. But this is always true for a lot of other systems as well. Think about, for example, the translational dynamic. So, like something that's moving, right? Um, what you have is you have that velocity flows from one place to the other, right? So you have that when you're moving out of one spot, you're going into the other. And so the total amount of stuff, if you have, say, a fluid moving from one volume to the next, the total amount of stuff, that velocity of stuff is always summing to zero across it, right? That's conservation of matter. And then the other thing is that you have that your forces are equal, right? If you have two pieces that are directly connected to each other and you push on one, then you have an equal and opposite force exerted on the other. That's Newton's third law. And it just turns out that this idea of there's, when you're defining how things are connecting, you have some things that are always going to equal each other, and some things for which on and connections are summing to zero. This is a conserved quantity across many different parts of physical modeling. And so then this is what we use, right? This is our foundation. So what we say is, okay, the pin of an electrical object is something that has a voltage and something that has a current. Where voltage is, when you connect them, they're equal. And currents, when you connect them, they flow. So therefore, the sum of currents is equal to zero. That's what this connection of flow means. And so then what we say is like, oh, every device is what we call a one port, which is something that has two pins, a positive pin and a negative pin. And so the voltage of the object is a voltage drop across the object. The current of the object is just the current flow through the object, which has to be conserved, right? I'm going through this a little bit quick. Again, I have a full 3-hour version of this. But so the idea then is like, this is now the definition of every possible electrical object that has two pins, right? And so, what is a resistor? A resistor is something for which all of these equations are true, and it satisfies Ohm's law, right? And so we just say, oh, we just say extend our previous model one port with this new equation, Ohm's law, right? So it should start to look like very object oriented, inheritance kind of type of feel. And so we just say, okay, these three equations plus Ohm's law gives you a resistor. Those three equations plus this plus the capacitance equation gives you a capacitor. And so, similar, you can say, okay, this is ground, this is constant voltage, yada, yada, yada. But when we can then connect all of these things together, what we end up with is we end up with a set of all the equations that define our complete system. Now, what does that look like? What that looks like is, well, at every single possible connection point, we have to say, well, the currents are summing to zero, so this current equals the negative of the other current, right? So the current coming out of here is the current summing into here. You have that so basically all these things I just stated as true, that's just what's listed here. There's about 20 different truths about our system. And so this is what we get. And so within the eight causal modeling system does is we say, okay, if these are all the truths, then then at the end of the day, I can simplify down the model to just this one ODE. And from this one ODE, I can recreate all of these other equations because of the underlying equalities I have between them, right? Which means the symbolic aspect to this is really central to how it works, but you can really just understand it as this is a way of modeling where what I do is I just state what's true, and I don't try to write down the code for computing it. The code for computing it is a one-time kind of thing. The thing that is actually reproducible and composable is the truths about what it means to be a capacitor, what it means to be a resistor, and what it means to be a voltage source. And now I let the system find out how to do the computation from those set of truths, right? So now what do? Is we take the set of truths, we find the equations we're supposed to have, and then we generate that to Julia. So why do we generate that to Julia? Well, the reason is because this gives us a language in which the speed of the code can be relatively fast, but then the size of the code that we're generating and the size of the equations that we're doing are relatively small, which makes it so that way it's kind of easy to look at the kinds of equations that you get. It's easy to look at the code that we're generating, but it's also we're not sacrificing any speed, right? So you could generate to say something like C, but then it'd be very difficult to understand some of the code, especially when it's, in putting in interpolations and doing automatic differentiation and all these other aspects as part of this, generated like, oh, this is the best way to solve the system. So we're able to have Julia be a reference standard, so that way the code that we're generating is both high level, but it's also rather fast. And the community is growing. There's a lot of metrics to be able to show that, for example, Julia is small in comparison to something like, say, Python, but we do have an estimated user base of around 1 million folks, which I think 1 million is probably larger than a lot of people would have expected for the word small, right? It's quite, it's actually gotten quite substantial at this point. And what we do with this is, after we find out what type of equation is the optimal form to be able to solve this problem, what we do is we do this code generation um, to be able to use either the linear solvers, nonlinear solvers, differential equation solvers, integral methods, or optimization libraries, which are all unified through a single interface in what's known as Julia SciML, right? And so, you can kind of think about this like SciPy, but this is a library that is spanning this whole space with a single interface that is also fast and is also able to be compatible with automatic differentiation, and it has all these special tie-ins, so that way all those things I mentioned about with symbolic indexing work, right? So if you can think about it as, it's like you had, PyTorch, and you had SciPy, and you had SymPy, all as one library working together, right? And that's why we kind of have to target in Julia, because the ways to be able to compose code in Julia is actually pretty essential for being able to pull off this kind of modeling tool. And at the end of the day, we're really not sacrificing speed. There's a lot of different published articles we have about the performance we get out of the ODE solvers. We have a lot of very active research. And actually, if you come to this next JuliaCon, I'm actually proposing a mini symposium where we're going to be talking about even some of the newest ODE solvers that are continuing to push forward this performance, right? So at the end of the day, the code that we generate is usually some kind of differential equation, and we are able to hit a lot of performance here. And just kind of highlight this kind of performance, I do want to point out, for example, that we have very fast code gen to things like GPUs. In fact, we were able to demonstrate in peer-reviewed publications that we're able to be about 20 times to 100 times faster than Jackson PyTorch in our GPU generation, because we do not make use of just pre-generated kernels. We're actually able to generate kernels on demand for new devices and new equations, which is a very deep kind of subject as to how the AI libraries and machine learning libraries are doing GPU computing is using a set of predefined kernels. But when you have these nonlinear systems, you really don't want to do that approach. And we're able to demonstrate that you get about 2 extra orders of magnitude in this type of domain when you really take into account the domain specific characteristics of how GPU compute needs to work. And so, at the last 2 minutes here, what does this look like in practice? Well, really want to highlight this project with Brad Carman, which is at ITW, or this company called Instron. So what they do is they work with these car catapults, which you put a car on the sled and you push it back. And the reason is to be able to test the forces on a crash dummy, to be able to see whether if I was to crash this car, does the safety system actually satisfy the requirements, right? You do this because you don't want to keep on crashing prototype cars because they're expensive to build. And so you want to be able to get the safety systems correct before you ever crash a prototype car, right? And so, but the key here is that you need to be able to model the system, because what you actually control are these hydraulic pistons that then push the sled. And so you have to figure out, how do I do the hydraulics correctly, so that way the way that the sled is moving acts like, for example, a car crash on the highway, right? So in 65 miles per hour, then goes to 35, yada, 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 a very specific acceleration curve. And so what they had done before is they used Simulink and MATLAB, and to get to the point of the story, they had switched over to ModelingToolkit because of the performance improvements over the previous things that they saw with Simulink. And again, Brad Carman actually gave a talk on this at JuliaCon 2022. So if you want to see this in a lot more detail from the word of the mouth of the person who did this, please go check out that talk. but they saw some massive performance improvements over what they were using before. And in fact, what they're able to do is they're able to then start to refine the model for the hydraulics. And once they understood the model for the hydraulics a lot more, they realized that actually they didn't need two of these, right? One to be able to do the fine grain tuning, one to be able to do the coarse grain tuning like you have on a microscope. They found out that if you actually do enough computational tuning of this project, you can actually completely delete this and sell a much smaller object for that is able to still meet the customer needs. And so,
Yeah.
what
Thank you,
we
Chris.
basically from having a better modeling system, they're able to then cut out about half of what they actually are using in practice on a multi-million-dollar machine. So the high
Yeah.
level point then is that Modeling Toolkit is a modeling system built around doing symbolic numerics, and it does it in such a way so that way you don't have to do the process of actually trying to figure out what code to simulate. And we're doing all these things at a generic level and finding that anytime that you're really thinking like, here's the trick I have to do, there's probably a more general way to think about that trick. And if we turn it into a symbolic pass, then we can retrieve that best hand optimized code at the end of the day through a generic modeling system. So hopefully that's a new topic to you, and this is kind of a fun kind of little detail. And if you want to talk anything more about Modeling Toolkit, I'm happy to chat with anyone. So thank you very
Yeah.
much.
Yeah, thank you, Chris. We're just about at time. Just one quick question for me is there R or Python interfaces to Modeling Toolkit like there are to ODEs?
So not to the full modeling toolkit, right? I will say this though, right? So because modeling toolkit is a good code generation device to Julia, one of the things that we do use is that, for example, in diffie-qpy, we in diffie-qpy we do actually have a function for JIT compilation, right? And the way that this de.jit actually works is it builds a symbolic representation of your Python code, and then compiles it to Julia, and then uses that JIT compiled form. And remember, right? I said that the GPU computing is so much faster than something like JAX. We do have, for example, this Colab document which shows, for example, that in Python, right? So in Python we can take a Python described ODE, we can JIT compile it to Julia, and then we can run it about 10 times faster than JAX on GPU in from the Python interface itself, right? Just by doing this translation via Modeling Toolkit. So we haven't been able to expose all of Modeling Toolkit to Python, though we have been able to expose certain aspects of it to be able to do this JIT compilation, to be able to be an accelerator over tools that are missing some performance like JAX.
That's amazing, Chris. We're going to close out the session. If you want to talk to Chris, you can. We'll make sure to post his contact information in the news feed. If you want to continue in the AI track, there's a generative AI talk which just started 2 minutes ago. If you want to continue with Julia, there's Jeff Sanson is now talking about static compilation in the general track. So thank you, Chris. Thank you, everyone, for coming.
Thank you so much for having me.
Appreciate it. Yeah. See you later.